Hi, everyone. On Wednesday, I was talking about hash tables, and I'm going to pick up where I left off. You might recall that I talked about how you have some object you want to store on a hash table. You call it the key. We need to first convert it to a number, which is called a hash code, that we can use to represent the index, and then we compress that to give us the actual bucket where we're going to store the item between 0 and n minus 1. And so there are two different functions here. The second function is the compression function. And the first function that maps the key to the hash code is just called the hash code. So if your key is an integer, then sometimes the hash code is really easy. An integer can be its own hash code. But if you have something like a string is not a number. You need to convert it into a number. And so let me start off by showing you a good hash code for strings. So we're going to take in a string called key. We're going to convert that to a number. So I want to return a hash code, which I'll store in hash val. And there's several things I want out of this hash code. I want to make sure that if I choose two different words, even if they're similar to each other, it's very likely that they will hash to different different numbers. Because I don't want to have collisions, I will often use words or strings that are very similar to each other in a lot of applications. And I want to make sure they don't wind up in the same bucket, or at least that the probability of that is low. So what I'm going to use as my strategy here is I'm going to treat the string as if it were a base 127 number, and then just convert it to an internal int in base 127. But I'm going to do one extra thing, which is, well, first of all, if it's a long string, then the base 127 number won't even fit into hash val, which is just an int and just has 32 bits. And the other thing is that I like a hash code to mix up the bits. Since there's going to have to be some conflicts, I want to mix up the bits in a complicated way that reduces the likelihood that two similar keys will hash to the same item. And for that, taking the integer modulo a prime works rather well. So having said that, here's my hash code. I'm going to go through all the characters in the string. And one character at a time, I'm going to add it to the hash value. So I do my base 127 conversion, which means I multiply the existing value by 127, and then I add in the next digit. Charat is a method that's defined on all strings, and it looks up the character at position I and returns it. And you'll recall I said last lecture that Java allows you to treat characters as if they were numbers, so you can mix them with ints. So I can just take a character and add it to an int, and it just uses the ASCII value of the character, or more generally the Unicode value of the character, if it's not an ASCII character, and adds it in to the integer. But I'm not done yet, because I also want to mix up the bits a bit and make sure that the size of this number doesn't overflow the 32-bit int. So I'm going to take the whole thing modulo a large prime. It's large enough that I'll get lots and lots of different hash codes, but it's not so large that it will let hash val ever overflow the 32-bit integer. So that's why I picked that particular prime. And then I just do that once for each character and return the mash that I get in the end. No, because that's just the first step. What I just drew here is this function here, the hash code. And then after this, then we'll apply the compression function as usual, which I talked about a good compression function at the end of the last lecture. So we'll just use that one. And that'll map us down to any number of buckets we want. And big N, the number of buckets, doesn't even have to be a prime number, because, well, we've already done mashing up the bits with a prime number, and now we can just take whatever comes out of here modulo n, and even that is going to be a good bucket to choose. All right, so this is a good hash code, but why is it a good hash code? Well, I told you last lecture that hash codes and compression functions are a bit of a black art, and the main reason why this is good is because nobody can find any flaws in it, and because it seems to work well in practice. And that's not an entirely satisfying answer, but what I'm going to do is I'm going to show you some bad hash codes that you can use for comparison and get a sense of how easy it is for a hash code to go bad. Yes?
The reasoning behind 127 is because there are 128 characters?
Well, so in ASCII, usually you just use the first 127 values or so. Now, if you have Unicode characters, like if you've got kanji characters in your string, then that's not true. They're going to be overlapping bits, but it's still going to work out. My main thoughts in choosing 127 were, first of all, to make sure that the digits, each digit has a different effect on the final number that we get. Sorry, each letter, each character has a different effect. So the last character and the second to last character, if they're both C, they will have very different effects on what number we get. And second of all, I wanted 127 to not be a power of 2 because, well, I guess it doesn't really matter in this case because I'm doing this modulo. But what I really want is for this number and this number to be mutually prime. And I will show you in a minute what goes wrong if they're not. Does that answer your question? Yeah. Okay. So for comparison, just to see what can go wrong, let's look at some bad hash codes on words. So these are bad hash codes on strings, but they're particularly bad if those strings happen to be English words, or words in probably any language, and I'll show you why. Now, the thing about English words is that you're not likely to get any string of characters with equal probability. Some letters come up more often than other letters. Some letters go together more than other letters. And so you've got these systematic biases in your data that the hash code is fighting. The goal is to make sure that those systematic biases in your input will not turn into collisions when you run them through the hash code. And it's easy to invent a bad hash code where that happens. So what's one of the simplest ways you could convert a string to a number? You could just add up the letters. So I could convert all the characters to ASCII or Unicode or whatever and add them all up. So you do get a number that way, but here's what's wrong with it. Words tend to be short. I mean, you don't typically find 1,000-letter words. And if I want to store an English dictionary with maybe 700,000 words is roughly what's in the English language, and store that in about 700,000 buckets, this is going to give me a lot of collisions because the sum is virtually always less than 500 or so. So for most English words, this will rarely exceed 500. So no matter what your compression function is, you're going to wind up with 700,000 words all bunched up in about 500 buckets. A few of the really big words will escape and get their own bucket, but for the most part, you're going to have a traffic jam all in a tiny piece of your hash table. Another thing to think of is that, in general, adding things together like this is just a bad strategy because it doesn't depend on the order in which those things occur. So, for instance, anagrams will always collide in this scheme. And it's very common in English or any language to have lots of words that have the same letters. Like pat, apt, tap, all collide with each other. So just adding things up is bad. And that's why in our good hash function, we make sure that each character gets treated differently depending on what its position is in the word. And so that's part of what this is meant to do. A second example of a bad hash code is, let's just choose the first three letters in a word. And then we don't even need a compression function if we use 26 cubed buckets. So that gives me a nice way to fill out a hash table of, maybe 100,000 buckets. The problem with this scheme is that, again, you have these systematic biases in English where, for instance, there are lots and lots of pre-words, or lots of words that begin with P-R-E, for instance. That part of the dictionary goes on for several pages, typically. On the other hand, there are no words that begin with XZQ. So just because of the systematic biases in the English language, this is not going to work out well at all. You're going to have lots of collisions again. And you're not going to come anywhere close to our ideal of having a nice, even distribution of keys through the buckets and every word pretending that it's hashed to a random bucket. As a third example of a bad hash function, suppose that we take our good hash function right there, and we just change the prime modulus. Well, to give the stupidest example possible, suppose I change the prime modulus to 127. What goes wrong there? Well, basically I'm taking a number, hash val, I'm multiplying it by 127, I'm adding a new letter, and then I'm taking it modulus 127. So what happens then? The hash val just disappears. This part's gone. All that's left in the end is the last character of the word. Because in general, 127 times hash val modulo 127 is equal to 0. Now, that's the most obvious blundering example you can make, but there are more subtle examples you could make where maybe this isn't 127, but you choose this number and this number so that they're not relatively prime. If they have a factor in common, then your output will be biased along that factor. Like, if they both have the factor of 7, then the remainder of your hash value, when you divide it by 7, will be determined only by the last character. And that means you're not getting as good a mixing up of the bits or a mixing up of the different characters in the word as you would ideally like. You can also have systematic problems where maybe, for some reason, you have an application that only produces keys that are divisible by 7, in which case you're completely wasting a few bits worth of information because you'll always wind up with a hash value that's divisible by 7. And so 6/7 of your buckets won't get used. What's that? So any questions about any of this? Yeah. Well, if they're not relatively prime, like suppose these two numbers have a common factor. Let's suppose that common factor is x. Then the hash value you get in the end is going to be of the form of ax plus b, where b depends only on the last character of your word. And so what that means is that the last character of the word is going to have more influence on what this number is than any of the other characters. And that tends to magnify the bias of, well, some characters appear a lot more than others. E appears as the last character of a lot of words. Q appears as the last character of very few words. And so that bias gets magnified, and that increases the probability that you'll have two words collide. Other questions? Yes, sir.
I know you said 127 because that's what you said something about our characters and having a value of 0 to 127.
Uh-huh.
So what would be the difference if I would have 2 there instead of a 127? Because they are mutually exclusive, right?
Right.
How would it make a difference in our
Good question. If that number were 2, well, right. Okay. Well, so the number you pick here, I don't think it's a good idea to make it too small because you come back to this problem again. If that number is 2, then summing the ASCII values, well, as we've said, that rarely exceeds 500, so we aren't mapping our words into a lot of different buckets. The same problem occurs if this number is 2 or 3 or 4 or 5. I mean, we get more than 500 buckets now. Maybe we get 1,000, but we're still not using all of our buckets. And even if you do make this number big enough that we are using all of our buckets, maybe we're not spreading out, maybe we're not approaching uniform probability distribution yet. So you do want this number to be on the big side, and that's the main thing I'm concerned about. If this number is, say, 127 or bigger, if you pick a bigger prime, maybe in the thousands or 10,000s, as long as it's mutually prime with this, then it'll still be a good hash code. So pick any prime you want for that number, just don't make it too small. Other questions? So once again, the reason this is a good hash code is just because we can't find any flaws in it, and it works well in practice, and it doesn't, we can't, all the obvious flaws that afflict most of the hash codes you would think of first don't show up in that one. But it is still a black art, and I cannot give you a formula for determining for any hash code whether it's good or not. But you should at least be aware of what the most common flaws are. And there's a lot of research that's been done on hashing and how to do hashing effectively. And definitely we don't have time to get into that in any detail in this class. So on to the next fact about hash tables. So one of the nuisances of hash tables is that their performance depends on the load factor. Maybe you have an application and at first you think you're going to get 1,000 items stored in your hash table. So you create a hash table with 1,000 buckets or so. And now all of a sudden your application starts running, and oops, it looks like you estimated wrong. There's going to be 1 million items you have to store in the hash table, not 1,000. So you're going to have 1,000 items on average in every bucket, and you're going to have a really slow hash table unless you do something. And so the something we do is when we discover that we're going to get more items than we had anticipated, we resize the hash table. So if the load factor, which you'll recall is little n over big N, where little n is the number of entries we are storing, and big N is the number of buckets we have to store them in. If that gets too big, then we lose constant time performance. So let's fix it. What we're going to do is we're going to have a strategy where we have a certain load factor target, and if we go over it, we fix it by enlarging the hash table. So let's do it when the load factor exceeds some constant, some small constant. I'll call that little c, and typically c might be 0.75. You could go a little bigger than that as long as you're using chaining. There's more than one way to deal with collisions in hash tables. There's another strategy I did not tell you about and won't be lecturing on called probing, but it is discussed in Goodrich and Thomasia if you want to know about it. You definitely don't want to go bigger than this for load factor if you're using probing. If you're using chaining, you can go a little bigger than that, but you want to prevent it from going above 1 or 2 or so. And so as soon as you insert the item that puts you over the threshold, we're going to allocate a whole new array to hold our hash table. And the new array should be at least twice as large. As the old hash table. So we're about doubling the number of buckets here. Then finally, we want to walk through the old array find all the entries that it stores, and rehash them into the new hash table. Now, let me give you a little warning here. You cannot just take the chains in the old array and copy them to the appropriate places in the new array. And the reason why is when you resize a hash table and double the number of buckets in it, you are changing the compression function. So you can use the same hash codes if you want, but your compression function has to change because you're no longer mapping your hash codes into n buckets. Now you're mapping them into 2n buckets. And that means that a lot of your items, a lot of your entries, are going to go into a different bucket than they did before. So you can't just copy them blindly. You actually have to go through each item in the old hash table, recompute its hash code, compute its new compression function, and then move it into the new array into the right bucket for the new array. Any questions about that? You also have the option of shrinking hash tables. So you definitely want to resize them up if they get too full, but you also might want to resize them down when they get too empty. For instance, you might do this when the load factor drops below 1/4. And the purpose of doing that is just to free up memory so that something else can use it. This might not be worth the trouble if you have just a program that runs quickly, does one big computation, and then quits. But if you have a program that's designed to be left up, like a peer-to-peer networking program or a music playing program, then you don't want your program to be taking up memory that it doesn't have to, because the person's going to be using their computer to run other applications at the same time. So this gives you one way to free up memory when you suddenly realize you're not needing it anymore. Now, there's the question of performance. Normally, hash table operations usually run in constant time, on average. But when you resize a hash table, obviously resizing a hash table does not take constant time. It takes linear time. So every once in a while, you'll do a hash table operation, and you'll realize you have to resize, and that one operation can take linear time. And so you might ask, is this ruining the performance of my hash table? And the answer is not really, because this is only going to happen about one time in n. So sure, you have to put up with one slow operation, but then you don't have to do that slow operation again for a long time. For a big long time after that, each hash table operation is going to take constant time again. And so you can amortize the cost of this resizing over lots and lots of operations. And so you get fast performance overall. And there is a formal mathematical way of studying that called amortized analysis. And we're going to learn that late this semester. I'm not going to discuss it anymore, but the quicken message is that the hash table operations still take constant time on average. Even though a few of them are very slow. Questions about that? Here is one application of hash tables. One of the inefficiencies of game tree search is that it's possible to reach the same board through two different directions. Like, coming back to tic-tac-toe, I could start like this and add an X here, and the opponent adds an O here, and then maybe I add an X here. Or this could unfold in a different way. Maybe I start by placing an X here, the opponent places an O here, and then I place an X in the center. So look, there's one board at the bottom that we can reach through two different sets of moves. And so what standard game tree search will do is it'll search through the tree, it'll find this game board, and it'll score it using minimax, and that'll take time. And then it'll come back through backtracking, and later on it'll recursively come down and explore this path, and it'll hit this board again. And then it will score that board again by minimax, which will take a long time. If this is a game that's more expensive than tic-tac-toe, like chess or network, then this can be really costly. And you'd like to avoid it and only have to score this board once the first time you encounter it. So hash tables give us a strategy for doing that. What we can do is we can use a hash table to remember all of the boards that we've ever encountered, say at depth 3 or greater, and keep scores for those boards so that we don't have to recompute them if we find them again through a different route through the game tree. So, let me write down the core of this. Some grids can be reached through many different sequences of moves. And when I say many, in the limit, I really mean many. When you're going down, in this example here, there's 2 ways to get to this board. But if you're searching to a deep depth, like a depth of 5 or 6 or 7, the number of different paths you can get to a certain board by increases exponentially with the depth of the tree. So, at depth 10, there might be millions of different ways to get to the same chessboard. And so you really want to only score that once. But it will be checked many, many times. So what we're going to do is we're going to maintain a hash table of previously encountered grids. Now, you don't necessarily want to store all of the grids in this hash table. In most 2-player games, you can only get duplicates at depth 3. Somebody has to make at least 2 moves before you're going to be able to get to the same board in 2 different ways. So there's no point in storing hash tables at depth 1 or 2 of your game tree unless you have a game that allows you to make moves where you don't actually move anything at all. Yeah?
Well, in that one, players can move shift.
Mm-hmm.
For example, it's possible to reach the same board at the depth 1 and then at the depth 3.
At depth 1?
Well, since move shift, instead of adding it down,
Uh-huh.
it's possible to have the same board at different levels.
Okay, that's true. That's true. You could return to a board at depth 4 that was the board you actually started with. That's right. So yeah, that is true. In that case, then maybe you do want to hash all the. If you're searching to depth 4 or deeper, then maybe you do want to hash all of the boards in your game tree. But only when you get to the step moves. All right. So when you hash a board, the key that you're hashing is the grid, and the associated value that you store alongside the key in the entry is the score for that grid. So dictionaries aren't just used to store words in their English language definitions. They can also be used for all kinds of things, this being just one example, where now you treat a game board as the key, and the definition suddenly is now the score for that game board. So to make this work out, then, your minimax algorithm has to take advantage of and use that game tree. So the minimax algorithm now, whenever it visits a game board, or at least visits a game board at the right depth that it might be useful, it checks if each grid it visits is in the table. And if the answer is yes, that grid's in the table, then you just return the score that's in the table, and you save a lot of time on not having to do minimax again from that game board. But if the answer is no, then first of all, you evaluate the score as usual by running minimax recursively, or by using your evaluation function if you've bottomed out. And then you store it so that if you encounter that board again, you'll have that number on hand in your hash table. Yeah. There we are.
So no matter how deeply the game you're at, if it's search depth 4 or 7,
Mm-hmm.
that's not actually get the same board. It's going to be the same board for it.
Well, sort of. So there's some complications here. So the question is, the score for the board is the same no matter what depth you encounter it at, right? Well, not necessarily, because the boards you encounter deeper in the tree, you are not searching them as deeply as the boards you encounter near the top of the tree. So suppose that I'm going through the tree and I encounter a board at depth 7. So there's my game board at depth 7. And maybe I only have time to search 7 levels deep, which actually means I have a lot of time, but you got to bottom out somewhere. So I just apply my evaluation function, and I get a quick and dirty evaluation of that game board, and I store it in my hash table. Now, maybe later on, I encounter that same board at depth 3. If I encounter it at depth 3, I probably don't want to use the value I took at depth 7. I probably want to actually run minimax down 4 more levels and get a better estimate of the board, because the estimate I calculated at level 7 just isn't accurate enough for level 3. But if it happens the other way around, if I encounter this one first and then I encounter this one later, that's a really good thing, because that means I get a really good depth, evaluation of the board, and I get to use it way down deep in the tree, so it's kind of like getting extra accuracy for free. Yeah?
So let's say you have a set search depth. You cannot evaluate your board past that depth.
You can do whatever you want. So if you have a set search depth in the project, then we require you to search to at least that depth. But in practice, people who write serious, hardcore computer chess programs that really play well, they usually use an adaptive depth, which means they're searching much deeper in some parts of the tree than in others. Really good chess programs know how to tell between boards where it's very clear who's winning and boards where it's not so clear who's winning and you really should search deeper. Yeah. Well, yeah. So if I call your machine player constructor and say depth 3, then that machine player had better be searching to at least depth 3. If it's searching to depth 4, I'm not going to know the difference, right? Maybe I'll just think you have a really good evaluation function. I can't tell the difference. But if you say you're searching to depth 3 and you only search to depth 2, and you miss the fact that you have a win at depth 3 and you make the wrong move, I'm going to notice that. Yes?
When you search the tree and you don't get all the way to the bottom,
Uh-huh.
do you know the value of that board if you don't search further and find out if it's a win or not?
What was the question?
Say you are searching down the tree,
Uh-huh.
and say you search down 3 to the one at 3, right?
Right.
That doesn't end the game for either player. It's then how would you know if that board has a value of -1, 0, or 1?
How do you know what value this has? You just keep searching deeper.
If you only search the 3, you don't search any further.
In this case, we use an evaluation function, which guesses what the number should be. Yeah, so, and that's part of your project, too. Yes? So, a good algorithm to make a hash code for a tic-tac-toe board is the question. I would say that I would just treat the hash table as a base 3 number. Like, for instance, you could use 0, an empty square I would encode maybe as 0, An X I might encode as 1, and an O I might encode as the digit 2. So that means each square is one of 3 digits, 0, 1, or 2. And since I have 9 squares, now I just concatenate those squares together into a number. That's a base 3 number. Every unique tic-tac-toe board is going to be a different base 3 number. Now I just convert that to an int using the algorithm that your TAs should have showed you in the first week of discussion section. Other questions? Okay, there's one last detail that you should keep in mind, which is after you make a move, you should empty the table and start fresh, probably. Why do I say that? Well, suppose that you've just searched a whole game tree to depth 7, and you've stored all of these boards into your hash table with evaluation functions for each of them. And then you decide you're going to make your move. So you make the move, and you decide to make that move, because that seems like the best move. Then your opponent makes a move, and you wind up here. Okay. Now you want to do game tree search from that board, which is 2 moves on. Well, you've already got every board in that game tree cached in your hash table right down to a depth of 5. So you could just reuse that. The problem is you've only searched now to a depth of 5, and you really want to search again to a depth of 7. So all of those numbers that you've got stored for all of the boards in this game tree are basically obsolete because you didn't search deep enough. Now, if you're clever, you might come up with some clever way of reusing them, but I would advise that you probably should just empty out your hash table and redo all of these boards to a depth 2 deeper so that you have more accurate numbers for them. So that's all I have to say about hash tables for now. We will come back again to them late in the semester when I talk about randomized algorithms and amortized analysis. Any questions about hash tables now?
Well, I have a question about the project.
Uh-huh.
We have a 5-second time limit.
Uh-huh.
We learned earlier in the year that Java garbage collects kind of randomly.
Uh-huh.
Garbage collection is slow. So if it just so happens that garbage collection happens during our 5-second limit, that could potentially bump us over 5 seconds, even though it's not our fault. It's garbage collection.
I think it's not all that likely to be an issue. It never has been before. Okay. But at any rate, if you really want to make sure that you're doing the maximum amount of work you can in the amount of time that you have, then you should probably have a timer in your code, and when you see that you've reached 4.9 seconds, it's time to close down shop. Yeah. And, garbage collection is not, it's not like it's going to suddenly pause for half a second. It's not that bad. Garbage collection is better implemented than that, so I don't think you have to worry. Question? About what? Yeah, so somewhere in the Java library there's a way to time your programs down to the millisecond. Absolutely, for sure. This is if you really wanted to have a good machine player that uses 5 seconds wisely, you really should be checking the timer. All right, what have we got? So I want to quickly go over a completely unrelated to hash tables thing, which is just the data structure stacks. So a stack, you should know what a stack is and what it does. And I'm not talking about the program stack anymore. I'm now talking about stack data structures, which are related. A stack is a crippled list, and it has 3 main operations. You may push a new item onto the top of the stack. You may pop an an item off the top of a stack. And you may examine the top item of a stack. And yes, the methods that you call are called push, pop, and top. And here's sort of how they look like. We call them a stack because we like to imagine a stack of dishes in a cafeteria is kind of the standard metaphor. And then if I pop the top item off, two things happen. The stack changes so that the top item isn't there, and pop itself has a return value. It tells me what the top item is that I just removed, so I can do something with it. Likewise, I can push dishes onto the stack anytime I want. And I can query the top item on the stack without actually changing the stack if I want as well. Again, I said a stack is a crippled list. It's easily implemented using a singly linked list. And if your implementation is not totally stupid, then the push, pop, and top operations will all take constant time. Now, the question you might ask is, why are we learning about crippled lists? And the answer is that the limitations of stacks will often tell people you are talking to a lot of information about how your algorithm works. Now, that sounds weird. The limitations of stacks will tell other people how your algorithm works. Well, let me show you how that works with a very simple sample application where what we want to do is match parentheses. So in this sample application, I have a string that looks something like this. And I want to ask if those parentheses are all matched up correctly. Maybe there are words in between them too, but I can ignore those. In this case, they are matched up correctly if I drew it right. And so here's my algorithm. Scan through the string, character by character. And when you encounter a lefty, which means either left brace, left bracket, or left parenthesis, then what you do is you push it onto the stack. And when you encounter a righty, you pop its counterpart off the top of the stack and check that they match. So here's how you know if your parentheses are mismatched. Well, if you pop one off the stack and check that it matches and it doesn't match, so you have a mismatch, or you have an exception because you try to pop something off a stack that's empty, or if you get to the end of the string, you're all done, and the stack isn't empty, In each of those three cases, you know that your parentheses are not properly matched. Otherwise, they are. So, now coming back to the language of computer science, if you say to someone who's an experienced computer scientist, oh, well, I have an algorithm that checks that the parentheses matched. It uses a list. They'll say, huh? And you'll say, oh, well, it uses a stack. And they'll say, oh, okay. They'll just understand, you know. So saying that you're using a stack really does convey a lot of information because of the limitations of a stack about how your algorithm works. Any questions? See you Monday.